In this video, we want to point out a couple of properties of definite integrals that will be useful for us throughout the rest of this course and the next course, Calculus 2, as well as later courses. So the first one is pretty easy to see. If we have the integral between a and b of the function f of x dx, we know from the first fundamental theorem of calculus that's capital F of b minus capital F of a, where capital F is the antiderivative of the function lowercase f. If we took the definite integral between b and a of f of x dx and apply the fundamental theorem, that would then give us capital F of a minus capital F of b, which is equal to the negative of capital F of b minus capital F of a. And so therefore we can make this conclusion that when we reverse the signs of integration, that is, instead of going from a to b, we go from b to a, that changes the sign of the definite integral. Now let's see on the next blackboard another property which takes a little bit more work to justify. So what this property says is that if we split an integral at a value c, then the sum of those two split integrals gives us the integral we started with. This one's best proven using pictures, graphs, showing the two cases. So let's look first at our case 1. So case 1 is actually very easy to see from this graph. Our integral between a and c of f of x dx has area identified with a Roman numeral 1. And the second integral between c and b of f of x dx has the area identified in the picture, this picture that is, as region 2. And so it's easy to see that a to c is region 1's area, and that c to b is region 2 area. And so that justifies this result in this case. So in our case 2, with the picture drawn below here, our first integral between a and c of f of x dx is the integral across this entire region here between a and c. And so the area of that region would be the area of regions 1 plus 2. What about the area of this second integral that goes from c to b? Well, if we look at region 2, we see that region 2 is a region that starts at b and that goes to c. So this integral right here from c to b, let's look on the next slide and see that the integral from c to b is the negative of the integral from c, or from b to c. So the integral from c to b is the negative of the integral from b to c. And if we look back at our picture, in the picture we have b to c, and so what that tells us is that this second integral from c to b is the negative of the area of region 2. So if we combine this 1 plus 2 with this minus 2, we see we get that area 1 is the only thing that remains, and the area of region 1 is what? From a to b, right? The area of region 1 is from a to b, and so that gives us our result, the left side. So summarizing, in case 1, this theorem is proven because this region's area plus this region's area equals the area from A to B. So these two things added together are the right side, and the left side is A to B, whereas in case 2, what happens is the left side is, in case 2, the left side is from here to here, so let's tag the left side with a box, and the right side is 1 plus 2 plus the negative of 2, which equals region 1. So that concludes this video. Maybe we should write one more time the property that we've discovered here. And it is that we can combine two integrals together if the top limit of one and the bottom limit of the other match up. Then we can combine them as a single integral from the bottom of the first to the top of the second, and it does not matter whether that value c is between a and b or not, as we saw in the two cases. Here in case 1, c was between a and b, whereas in case 2 it wasn't, and we proved it in both cases. So there's the result. That's important sometimes to simplify integrals like these this way. Actually, sometimes we want to go, I should actually restate that. We actually use this theorem both ways. Sometimes we want to take an integral of the form of the left side and transfer it into the form of the right side, split it up into two. We do that in a proof, actually in the proof of the second fundamental theorem of calculus, and sometimes we want to take two integrals that are of the type on the right side and combine them together to get the single integral of the type on the left side. So sometimes one way, sometimes the other, depending on what our needs are.